In the previous session, we have looked at single phase voltage source inverter, both the half bridge inverter as well as H bridge inverter, and their operation in the square wave mode as well as the pulse width modulation mode. Now, in this particular video, we'll look at the operation of the three-phase voltage source inverter, which consists of three half bridges. So in case of a single phase inverter, we had a half bridge configuration, something like this. You had a half bridge and the load was connected to the O point. The load was connected to the O point. In this case, we are not connecting the load to the O point, it is connected to a separate neutral point, a floating point, which is distinct from the O point. The O point is not necessarily connected and it can be considered as a fictitious point. It's not necessarily a physical point to be accessed. So we have a VDC source and we can think of a positive, 0 and positive voltage, 0 and VDC, or with respect to the O point, we can decide like this is at 0 volt. In that case, this will be plus VDC by 2 and this would be minus VDC by 2. So with respect to the N, capital N, it will be plus VDC and 0. With respect to the O point, it will be plus VDC by 2 and minus VDC by 2. So we can decide how to operate it. However, at the output, what we look for is the voltage across the floating point small and neutral of the load and the VA, VB, VC with respect to that. So VA and VB and VCN is what we would like to look at, and based on that thing and the impedance, you will have the currents IA and IB and IC. Okay. Also, the current into each of the half bridge is designated as IA plus, which will be ISA plus and IDA plus together. It will be IA plus. Similarly, IB plus and IC plus, which are the leg currents. So these segments are the legs. Half bridge 1, half bridge of A phase, half bridge of B phase, half bridge of C. So this is leg B and leg C. And when the switch SA plus is connected, the node A that is connected to the load A will be connected to plus VDC by 2 with respect to the O point. And when SA minus is connected, SA minus is turned on, and when the current is appropriately, either SA minus or DA minus would be conducting such that the load is connected to the minus VDC by 2 with respect to the O point. So this is the operation which we have, and we would like to see how the outcome would be. And the minimum requirement for a three-phase operation is to have a three-phase symmetry, or they are shifted in time 120 degree with respect to each other. So VAO with respect to VAO, VBO will be 120 degree delayed, and VCO would be 120 degree delayed. And we say that the simplest operation possible for any inverter is a square wave mode of operation. So the possibility is that VAO could choose either VDC by 2 or minus VDC by 2. So we connect it to plus VDC by 2 for 50% of the first half cycle, and the second half cycle we'll connect it to minus VDC by 2, where T, which is 1 by F, or where the F is the fundamental frequency. F, if it is 50 Hertz, T would be 20 millisecond, and the node A would be connected to plus VDC by 2 for 10 millisecond and minus VDC by 2 for the remaining 10 millisecond. So this is the operation which we have said. So with respect to the O point, let me use blue color. So with respect to the zero crossing of the VAO, the positive zero crossing of the VAO, the positive zero crossing of VBO is delayed by 120 degree. The positive zero crossing of the VCO is delayed by 240 degree. So this is 120 degree and this is another 120 degree. So each waveform are 120 degree apart. And then we want to look at what is the line to line voltage, which is between these 2 points. So this is VAB, that is the line to line voltage. And we would also like to look at VA capital A small n, which is the VAN would be the phase voltage in the phase A. So we'd like to compute those things. So in case of the line voltage, it's fairly simple, because all you have to do is subtract this thing, because they are connected to the same, they are measured with respect to the same reference point O. So we have to just take the difference. Now we note that the voltage VAO is connected to plus VDC by 2 for the first 50% of the time, and minus VDC by 2 for the remaining time. Similarly, this is connected to plus VDC by 2 here, and minus VDC by 2 here. Or simply I can say that it is either plus or minus. So let me mark it here: plus here, minus here, plus here, minus here, plus here, plus here, minus here, plus here, minus here, plus here, minus here, minus here, so on and so forth. So when we take a difference VAO, all you have to do is we have to find out. So VAO in the first 60 degree, VAO would be plus VDC by 2 minus VDC by 2, that gives me VDC. So my VAB would be VDC in here, and then the next cycle again it will be VDC here. Then here again, if you look at this we have got VDC. The third 60 degrees segment we have is plus here, so it is VDC by 2 minus VDC by 2, that will give me 0 here. So the outcome is 0. And in the next segment, minus and plus here, so it is minus VDC by 2 minus again VDC by 2, so that will give me minus VDC here. And then again I have minus VDC by 2 plus VDC by 2, that's again minus VDC, and once again it's minus cancel, it will give me a 0, and this will be my waveform for VAB. So the magnitude here is either plus VDC or minus VDC. So this is the outcome. It's plus VDC or minus VDC. Now we need to identify what is VA small n. So VAN, if you want to find out, it is essentially VAO, which we already know. VAO is plotted already, it's a square wave, minus VNO. Now what is VNO? That we have to identify. VNO is what we have to identify. How can we compute that? So let's do the circuit equations. We know that if you look at the circuit thing, we know that at the node here it is VAO minus IARA or IARA minus LA DIA by DT minus or equal to 0, or in general if it is in the this is the equation. So any for any I'm sorry, this should be minus, this should be equal to so VAO minus VNO, which is the, okay, I think I made a mistake here. It should be, this is VAO minus VNO, that is the VAN, the phase voltage. VAN minus IARA, VAN minus IARA minus LA DIA by dt is equal to 0, which would mean that VAO minus VNO minus IARA minus LA DI by dt is equal to 0. Similarly for the B phase, VBO minus VNO, this is the phase voltage, minus IBRB LB DI by dt is equal to 0. Similarly, VCO minus VNO ICRC LC dIC by dt is equal to 0. Now we know that if it is balanced and symmetric, I can say that RA is equal to RB equal to RC is equal to R, and LA, LB, LC being equal to L. So if that's the case, if I add 1 plus 2 plus 3, what I'm going to get would be VAO plus VBO plus VCO plus 3 VNO, that will be equal to IA plus IB plus IC, IARA plus IBRB plus ICRC, but RA, RB, RC are the same, so it will be IA plus IB plus IC plus R plus LA, LB, LC, they are the same, so it will be L, and d by dt of IA plus IB plus IC. So that gives me the situation. So we know that IA plus IB plus IC is equal to 0 for a balanced situation for a 3-wire system. So we have VAO plus VBO plus VCO, which should be equal to 3 VNO, because the product, the sum of these 3 quantity will go to 0 here, and here also it will go to 0. The derivative of 0 is 0. So what you get would be VAO plus VBO plus VCO is equal to 3 VNO. So from there, I can show that the VNO is going to be VAO plus VBO plus VCO by 3. So we know VAO, VBO, VCO. All you have to do, add them together and scale it by 1 by 3. So this is my plus here, this is minus, this is plus. So I get plus VDC by 2, 1 get cancelled by this one. So what remains is plus VDC by 2, and again here this is plus, this is minus, so it will be minus VDC by 2 as an outcome, and all of them divided by 3. So it should be plus VDC by 6 minus VDC by 6. Okay, it's plus VDC by 6 or minus VDC by 6. So that gives me the VNO. Now this VNO is present in all the 3 phases, and that's why we call it as a common mode voltage. So what we want to know is VAN. We want to compute VAN, VBN, VCN, which are the load voltages, or what we call as a phase voltages, load phase voltages, and we want to get that, remove the common voltage from that, so that I can compute VAN, which is VAO, the leg voltage or the arm voltage or the pole voltage, because it's an SPDT switch with the pole being at the A point. So VAO is the pole voltage or the leg voltage. Okay, so that leg voltage minus VNO should be my VAN. So that is what we are going to do. So we got VNO as VDC by 6 or minus VDC by 6. So what we get here is 2 VDC by 3, that is VDC by 2 minus VDC by 6 is going to be 2 VDC by 3. So it will give me the shape like this, where this chopped off position correspond to the VNO. Okay, so from VAO we remove that part, so it will be actually 2 VDC by 6 and VDC by 6. Okay, so that's the voltage which we get here, and this we'll have we note that we have some more this voltage chopped off that correspond to actually the what we call as the common mode voltage, which just happens to be all the harmonics corresponding to third, 9th, 15th, 21st, etc. All this is also called as triplen harmonic. Okay, triplen harmonic, which we call triplen harmonic. So all the 3rd, 9th, 15th, 21st harmonics are removed by this cancellation, owing to the circuit connections only. So this is the line voltage, this is the phase voltage, and the third one, which is the original waveform which we generated, is the pole voltage of the inverter.